As we've seen, a limitation of perceptrons and other similar linear models is that they are linear. They can learn only a single linear hyperplane boundary. They're not able to learn more complex, non-linear boundaries in the original feature space, although it may be possible to learn such boundaries by projecting into an expanded basis. This limitation of linearity is a shortcoming of the model. It's not a feature of the learning algorithm. So, for example, the perceptron algorithm has other issues, but this is a shared one that it would share with any other way of learning a linear model. We can view logistic regression and softmax regression just the same as we can view perceptrons as a kind of neural network model. They take a weighted sum of the inputs, they apply some kind of non-linearity to the output in order to make a decision. In these sort of extremely simple neural networks, there is a single set of inputs and a weighted sum is taken across them. So there is a single set of weights that constitute the model's learnable parameters. With softmax regression, we see a similar neural network structure, but this time there is more than one output. There are the scores for each of the different classes, which will then be passed through the softmax function in order to evaluate the loss. There's still a single set of inputs and a bunch of weights in between. One way of interpreting the single linear decision boundary that comes out of any one of these weighted sums is as a new feature which contains some inferred information about the original feature space. And these features could subsequently be aggregated. We saw this with AdaBoost, where AdaBoost would take a weighted sum of the decisions coming out of a series of weak learners. And in doing so, it was able to construct a non-linear decision boundary. A natural way of applying this kind of aggregation with a neural network is to add further layers downstream that take in the inferred features from the earlier layer and then make decisions based on those. Doing this gives us the multi-layer perceptron model. In this case, there is more than one layer containing neurons and more than one set of learnable weight parameters governing how those inputs are aggregated. In principle, there's no reason why neural networks have to be wired up in layers. They could be connected in all sorts of crazy topologies, and in fact, there's some evidence that doing so can lead, in some circumstances, to quite efficient network structures. However, in practice, we almost always organize our neural networks in layers. Layers are a useful organizing principle. They divide the network up into distinct functional chunks that are easier to implement and that are easier to reason about. What actually constitutes a layer is somewhat up for grabs, but a very common way of thinking about it is a layer is a thing that has weights. It's quite common to represent the inputs and the outputs from the model as layers. These are slightly different kind of thing, and we don't always do it, but it's one way of describing the topology of the network. As well as being useful from an organizational standpoint, layers are also computationally useful. They allow us to construct an implementation that is efficient in terms of linear algebraic operations. The basic component here is the fully connected layer. It has some number of input neurons, some number of output neurons, and all of the inputs are connected to all of the outputs. Each of those connections has an associated weight. The input size is often known as the fan-in, and the output size is often known as the fan-out, for slightly obscure reasons, probably relating to the numbers of lines coming out of the input neurons and the number of lines going in to the output neurons. This kind of fully connected layer, in which there is a weight connecting each input to each output, can be conveniently represented as a matrix. In this matrix, which we will multiply by the input data on the left, the rows will represent the features or elements in the input vector, and the columns will represent the features or elements in the output vector. So the dimensions of the matrix will be fan in by fan out. If we have a single row vector of size fan in and we multiply that into this matrix, we get out a single row vector of size fan out. If we have a design matrix of inputs, which is n, the number of samples, times fan in columns, and multiply that by the weights matrix, we'll get out a new design matrix style representation of the output features, which again still has n rows, but now has fan out columns. If we were to chain together a number of these kinds of fully connected layers, we would be able to represent that as a sequence of matrix multiplications. However, matrix multiplication is associative. We could just bracket all of those matrices together, collapse them all into one, and we would have the same as just a single layer. Functionally, taking a weighted sum of weighted sums of weighted sums of the inputs is still just going to produce a weighted sum of the inputs. So somehow, by adding multiple layers, we haven't achieved anything. Why did this not present a problem for AdaBoost? The answer is that AdaBoost is not taking a weighted sum of weighted sums directly, but a weighted sum of specific decisions coming out of its learners. Those decisions are non-linear. They've had some threshold applied. It turns out that as long as we apply some kind of nonlinear transformation after each of our linear layers, then we will be able to model more complex nonlinear boundaries. In general, these are known as activation functions, and these are a part of what give neural networks their power. These kinds of nonlinear activations are comparable to the firing threshold in a biological neuron, although again, this is a very loose analogy because biological neurons are pretty much nonlinear all the way down. Given this structure of interleaved linear layers and nonlinear activations, we can build up much more complex multi-layer perceptrons. It is occasionally useful to conceptualize these nonlinearities as separate operations in the network graph, as separate layers in effect, so that you would have a linear fully connected layer feeding into some kind of nonlinear activation layer. But more commonly, we consider the activations to be rolled into the linear layer, and that makes for a more compact graph representation. So it's useful to think about what the hidden layer is doing. Each neuron in any layer is, roughly speaking, if we gloss over some details of the effect of the activation function, it's finding a linear decision boundary or a linear regression manifold in the space of the upstream features that are supplied to it, so the inputs that it's getting from the previous layer. In the first hidden layer, the inputs are just the raw features, and the layer is finding useful or interesting hyperplanes in that feature space. The next layer is finding useful combinations of those hyperplanes, and then the layer down from that will be finding useful combinations of useful combinations, and so on. This allows the network to build up layer by layer increasingly complex classification boundaries or regression landscapes. We can make the network bigger and thereby give it a richer processing capacity, both by making the individual layers bigger, having more neurons on them, which makes the network wider, and also by adding more layers, making the network deeper. A wide layer will generate a bigger range of candidate features for the next layer to aggregate, whereas a deep layer will produce more complex, nested aggregates of complicated compound features. Broadly speaking, we can add lots of neurons to make the network wider and deeper and really go to town. However, we've really kind of glossed over one important feature, which is how on earth can we train such a network? If you cast your mind back to the logistic regression derivation in week 2, we've seen that that constitutes a very simple neural network with no hidden layers and only the final output nonlinearity, and deriving the gradient for that and finding a solution was pretty complicated. This pales into insignificance compared to a deep network, so how on earth are we to fit this?